Wildfires are a global problem. You can appreciate this by looking at the following animation, made using the active fires recorded by the NASA Fire Information for Research Management System. As you can see, fires occur in all corners of the planet, spanning many different environments. This can make generalizing the problem difficult. To solve the problem, we must first understand it. One thing all wildfires have in common is that they start and they spread by ignition. Flaming ignition happens when the correct amount of air and gaseous fuel are in a mixture at a high enough temperature. When these conditions are satisfied, we see a flame, or in other words, a sustained combustion reaction. When the fuel is initially solid, the solid fuel must be converted to a gaseous fuel. This is often by a process called pyrolysis, which is the breaking of larger molecules to smaller and more volatile components. This is a temperature-dependent process, with higher temperatures leading to the generation of higher amounts of gaseous fuel. In fire safety engineering, ignition is often approximated and understood using a critical surface temperature. At this temperature, we have enough gaseous fuel being generated from the surface of the solid. Hence, if we model the temperature of the solid surface, we can define the time to ignition as the time taken to reach the ignition temperature. We do this by creating an energy balance. Heat is input into the system by radiation on the top surface. Heat is transported away from that surface and into the solid by conduction. As the solid heats up, its exposed faces begin to radiate heat to the environment. Furthermore, the surface heats the gases above it. This creates a buoyant flow, transporting heat away from the surface by convection. By solving these processes, we can approximate the ignition. However, in wildfires, the fuel is not solid, but is porous, and is made of individual fuel elements arranged in a fuel structure. This changes the heat transfer processes. The top surface is no longer well defined, and heat can be absorbed over a depth rather than just at the top. The fuel elements are less connected, changing the path of conduction through the material. As the material heats up, it begins to radiate as in the previous case. However, the exposed faces now not only face the environment, but also into the depth of the material. Additionally, the open nature of the fuel means that flows can be established throughout the fuel. The goal of my research is to investigate how the fuel bed structure affects the heat transfer processes and subsequently the ignition.